Hi, we are the data-centric AI team at Elucidata. In this video, we take up a problem that's commonly encountered by data scientists and their ML projects, the problem of missing data, and how thinking about the scope for data imputation could be a value-adding step in the modeling process. Let's consider this problem in the specific context of precision medicine. Briefly, precision medicine seeks to target heterogeneous diseases like cancer in a highly personalized manner. This strategy takes into account the genetic vulnerabilities of each individual to select the safest and most effective course of treatment for them. So how does this approach work in practice? The discovery process typically starts with screening a large number of cell lines representative of the disease against a wide range of candidate drugs. This large-scale in vitro information on drug responses, together with data on the molecular composition of the cell lines, informs ML models. These models are trained to use a cell's molecular profile to predict whether the cell will respond or be resistant to that drug. The predictive signatures or biomarkers of drug sensitivity discovered through such preclinical models can then be carried over to the clinical setting to potentially help decide the right drug for a given patient. Let's focus on the first step of this process, the screening that generates response data for tens of thousands of combinations of drugs and cell lines. These combinations can collectively be represented by a two-dimensional response matrix with white pixels indicating if the corresponding data point is available and black indicating missing values. It is quite apparent here that responses for several combinations are not available. In fact, there are drugs for which more than 50% of the screening data is missing. Now, why is this missing data a problem? Well, every row in this matrix is the set of labels that will go into training the prediction model for one drug. The more missing labels there are, the less the data is usable for modeling. And on general grounds, we expect gains in the quality of the trained models with more quantity of label data, like in this one example you see. So if we could somehow fill in these missing entries, make educated guesses to complete this response matrix, it might improve the consumption and the usability of the data. So there are two key questions here. One, is imputation of missing data possible to a reasonable degree? And two, will data imputation add value? That is, will it make data more usable and aid ML efforts to identify the biomarkers of drug sensitivity? So how does imputation work in practice in a way that doesn't just add noisy labels, but augments the available data? One way is to look for similar patterns in the response data here. These correlations could arise from chemical similarities between the different drugs screened or reflect the shared origin of different cell lines, which might be coming from the same tissue. So when we map the correlations between drugs and between cell lines, there is indeed considerable redundancy in the data, which could be tapped into to guess the missing values based on the available data points. So this is the basis for some of the statistical methods in use for data imputation. In fact, a larger scaled-up version of this problem finds application in ubiquitous recommender systems. So when you visit an online shopping website or a video streaming platform, it makes new recommendations based on your personal history. Under the hood are a variety of matrix completion methods which mine similarities in user patterns to predict individual preferences. So over here, the filling in or imputation is essentially the predictions about whether a consumer will like a particular piece of music or buy a product. So how does data imputation work in practice for our use case? Let's switch track and walk through a Python notebook illustrating this analysis. This is our Poly notebook. We start by loading all the required data sets as pandas tables. First up is the drug response data. Here we have taken up the example of GDSC, an anti-cancer drug screen from the Sanger Institute. The screening data is loaded as a table where each row corresponds to one combination of a drug and a cell line. The columns of this table provide various numbers, including the IC50 values, which we focus on for this analysis. Next, we load the metadata along with the molecular data, that is the RNA-seq expression profiles for the screen cell lines. These are sourced from the Cancer Cell Line Encyclopedia, CCLE. In this expression matrix, each row is one cell line, and columns stand for the gene expression features, which will be the inputs to the ML models. Next, we transform the loaded drug response table into a response matrix of drugs and cell lines. So this function takes the sequential response data as input and converts it into a matrix with drugs as rows and cell lines as columns. This matrix is displayed as a binary heat map, which immediately reveals the coverage of the data set. So missing response data is indicated by the black pixels. The drugs are arranged vertically in order of coverage. So drugs closer to the bottom have a lot of labels missing. These gaps in the data can limit its usability for identifying robust markers of drug sensitivity. So we next examine if imputation methods applied to this data set can help here. To begin with, we benchmarked a few imputation methods on simulated data where we artificially remove some labels and see if they can be recovered or imputed reliably. In general, these methods do reasonably well, and we find that methods based on matrix factorization fare generally better. So we pick the best performing method and apply to our use case, the full GDSE response matrix. The next code block applies matrix factorization to impute missing data in the full response matrix. So the goal here is to evaluate whether there is a value in performing data imputation. To do this, we carry out two experiments, which I will summarize one by one. In the first exercise, models are trained on the original data with missing entries to predict drug sensitivities for each drug separately. Then the missing entries are imputed, and the filled-in response matrix is used to train another set of prediction models. And these two sets of models, before and after data imputation, are compared to see whether imputation merely adds noise or can confer some benefit. As a first step, we define functions that fit random forest models to the data. Fivefold cross-validation is used to tune the model parameters. These are regression models, so they predict the IC50 response for a given cell line. The model's accuracy is captured in terms of the correlation between the predicted and actual IC50 profiles on a held-out validation dataset comprising 100 cell lines. The next code block demos a run-of-the-model training and testing for one drug. Cisplatin is taken as an example here. This step is next looped over 40 drugs at the bottom of that response matrix I showed earlier. So these are the drugs with the most missing response data and which can potentially be impacted the most by the filling in or imputation. Once these models are fit, we can compare the before and after model performances. These differences are displayed here. For each drug, we plot the percentage change in prediction accuracy after imputation. So two things stand out here. One is that there is an overall trend of improvement in the performance of these models after adding the missing labels. And two, these changes are statistically significant over several drugs. So overall, this preliminary analysis suggests that imputation isn't merely adding noisy labels, but can actually augment the data use. As a second exercise, we ask a related question. Does imputation improve the ability to identify predictive features in the data? Here, we are not tied to a particular model, but instead, we consider features which can be generic building blocks for different ML models and affect their performance. So the basic idea is that we take a drug that has lots of data labels originally, remove a large proportion of those labels, and apply imputation to the matrix as a whole. For each of these three test cases, we find the set of top gene expression features which are most correlated with the drug responses. And then we compare these feature sets, finding the overlaps O1 and O2. If imputation works reasonably, then O2 should be larger than O1. That is, the recovery of the predictive features should improve after label imputation. So the next code block implements this experiment. We take the top 100 drugs by their coverage in the screen and one by one perform this comparison between the original label data and the labels assigned by the imputation method. For each drug, the recovery of the right features is displayed as a point in 2 dimensions, showing the before versus after imputation outcomes, the O1 and O2 along the 2 axes. Any point above this diagonal line indicates that imputation of labels improves the recovery of features. And it's apparent for this case that adding missing data values, missing labels works generally. Nearly 90% of the drugs examined here fall above the diagonal line. So this exercise, taken together with the earlier one on model comparisons, indicates that imputation has a generally positive impact in this use case and adds value to the incompletely labeled data. This brings me to the end of this video. The purpose of this demo was to highlight missing data, which is common across pharmacological screens. These gaps in the data can be a drawback for its usability in preclinical models for drug response prediction. We suggest that thinking about the scope for data imputation in your biomedical project can add value to the modeling process. The potential impact of missing data imputation is likely to be even more when combining data from multiple complementary drug screens to create larger expanded data sets for clinical biomarker discovery. Thanks for your time.